295 megawatt hydropower unit does not move fast, it moves heavy. With a rated head of just 69 meters and massive water flow, this machine relies on volume, not height. Unlike high-head turbines, this unit generates power through sheer mass flow. And starting it is a completely different engineering challenge. Before rotation begins, we must lift the rotor. At 100 RPM, this unit uses a much larger diameter runner. That means greater weight, greater inertia. The thrust bearing supports hundreds of tons. We activate the high-pressure oil lifting system. Pressurized oil is injected beneath the thrust pads. The rotor rises slightly, only microns, but enough to create a stable hydrodynamic oil film. Without this lift, the start-up torque required would damage the bearing instantly. Now comes the most powerful part of this machine, water admission. At full rated output, this turbine handles enormous discharge. At today's target load of 250 megawatts, discharge reaches approximately 370 cubic meters per second. The governor sends commands to hydraulic servo motors. Guide vanes begin to open gradually and symmetrically. Because of the low head, water velocity is lower than high-head plants. But the flow volume is immense. Torque builds progressively, not explosively. Slow tachometer rising to 100 RPM, heavy shaft rotation. Rated speed, 100 revolutions per minute. Slow, but extremely powerful. At 100 RPM, with the correct pole configuration, the generator produces 50 Hertz, matching the national grid. Add mechanical insight. High rotational inertia makes acceleration smoother. But during disturbances, that stored energy becomes critical. Governor tuning at this stage is essential. Once rated speed is achieved, excitation begins. Direct current flows into the rotor poles, creating a rotating magnetic field. As the rotor turns inside the stator, magnetic flux cuts across the windings. Voltage is induced. For a machine of this size, excitation stability is critical. Even small voltage fluctuations can disturb the grid. Now comes synchronization. Voltage, frequency, and phase angle must match the grid exactly. Even a small phase mismatch can generate enormous mechanical stress. With such a large rotating mass, any sudden electrical torque shock is amplified. When the phase angle approaches zero and frequency deviation is minimal, the breaker closes. The machine is now locked to the grid, but we are not at full load. Today's operational target is 250 megawatts. Guide vanes open further. Discharge increases to approximately 370 cubic meters per second. Mechanical torque rises steadily. Electrical output stabilizes at 250 megawatts. Throughout loading, operators closely monitor thrust bearing temperature, shaft vibration amplitude, stator current balance, and hydraulic pressure stability. In low head, high flow turbines, hydraulic stability is critical. Sudden load rejection can cause speed rise due to stored kinetic energy. Protection systems continuously monitor overspeed, overcurrent, and abnormal vibration. This is how 69 meters of head and 370 cubic meters per second become 250 megawatts of controlled power. Not fast, not dramatic, just disciplined engineering. Real machines, real scale.